Okay, so for this week, I wanted to continue looking at specific applications of logic and computation in computer science. There are some ideas from logic, especially show up in all kinds of subjects. Here we're looking more specifically at the computer science end of it, rather than say the mathematical or philosophical uses of logic. So I wanted to talk about how logic and computation show up in the field of language design. I know some of you have been involved in implementing languages to various extents. Some of you have worked with parsers, for example, and parsing has this very nice theory and practice. It's a nice topic to teach in a compiler's module. Nice topic for people to do workshops on, exercises. Once you go beyond parsing, your compiler instruction tends to get a little more fuzzy. There's the idea that you've gone off and created a parse tree, something like this. This is a parse tree from a bunch of tokens getting put in. Often a compiler's course will end round about this point, and it ends with a statement like, then you can take your parse tree and use it to implement your actual programming language somehow. When you're building these parsers, there are very nice representations of BNF syntax we've talked about for defining grammars. And when you have that kind of grammar, you can then have automated tools that will pretty much generate the parser for you, like Flex and Bison. Again, it is much less clear what happens at the back end. How do we actually define what a language is and what we want a language to do? This is often done, or almost always done, in ad hoc, hacky ways. Even for the languages that we use every day, it's uncommon to be much more rigorous than that. And many languages are therefore defined just by having a reference implementation. It's whatever the designer of the language has written in their compiler that defines what the language is, which makes things kind of tricky if anyone else wants to implement the language and make claims that they have an equally valid version of the language. So operational semantics is a field, it's an application of logic and computation to describing languages. Both for humans to understand and increasingly for automated tools and machines to understand. So I'm going to tell you a bit about what semantics is, give an overview of how it works. Particularly when we get to functions, you will often come across semantic concepts in everyday life. If someone tells you that a new language is call by name semantics or call by value semantics, that's often where you'll come across these concepts. Types, we've discussed types earlier in the workshop segment. Types form another form of semantics. They're ways of understanding what a program is doing and placing restrictions in particular on what programs are valid. So syntax is one way of restricting valid programs. You can say any program that doesn't match our grammar, we're just going to throw it out and give a syntax error. But you might have programs that are syntactically okay, but are not semantically okay. And a good type system is a way of checking for that and throwing those errors out. So sometimes you'll get other errors from the compiler that are not syntax errors. You get these semantic errors usually coming from a type system. And under the hood, these are things you probably use every day in the languages you program in. Under the hood, there is a lot of logic and computation, at least in languages which implement these things properly. And some languages effectively have a full-on AI logical inference system just sitting there as part of the language runtime. If you're using especially languages with advanced type systems like ML and Haskell, that you pretty much have a full, almost Prolog-like AI sitting there that is working in the background, making logical inferences, especially about types and other forms of semantics. As with all these things, when AI actually works, it isn't called AI anymore. In that case, it just becomes part of the language design. It becomes part of the type system. But a lot of very clever stuff happening under the hood. So, why would you want to do this? I have. I'm not going to name any names. I can think of one compiler's project that is currently running that is not doing anything even remotely like this, and is simply coming along every week and hacking together a bunch of regexes and a bunch of x86 assembly instructions spitting out. It goes line by line through the code. It parses the language as a regex and it spits out a load of assembler, and it doesn't give any consideration to anything resembling logical computation. Compilers like that were developed for many decades. That's how compilers were originally written. Still are in some cases, but you will eventually reach a point if you're building a new language where the community decides it needs something more rigorous, and you need to agree on what the language actually is. You have many users. The users are using your language. They're also using each other's code, and so you have all these software engineering issues basically about who to blame when something goes wrong. I call your code written in his language and it didn't work. Whose fault is it? And implemented by her compiler. So four people can potentially be blamed, right? The end programmer, the library programmer, the compiler writer, the language designer. And as always, by having a rigorous definition of what's going on and whose fault is what, you can resolve those conflicts much more easily and quickly. So part of this is about human-to-human communication, right? Your language designer, the compiler writer, various types of users all have to agree on what the language actually is. And if you take a more engineering approach rather than a computer science approach, you will find language standards like C++ that have been attempts to do what engineers do in other fields. Engineers will write a standard for what is a screw. They'll define exactly how big a screw has to be and what are its tolerances and the shapes of the thread on it and so on. And they'll publish the standard, and then that defines what a screw is, or what that kind of screw is. There have been attempts to do this for languages, and I think you can still buy the C++ standard as a great big paper book, which many thousands of person hours have been spent trying to describe in English what C++ is supposed to do. Not necessarily the same thing as what it actually does, because you then rely on all these different compiler writers to implement that standard. And if they've got many thousands of pages of English to get right, it's somewhat unlikely that every single part of it will get implemented correctly. It's still common today to find C compilers that have things missing or done differently, or in some cases just not defined. There are gaps in the C and C++ standards which lead to undefined behavior, where a compiler designer can just do whatever they want because it's undefined. More creatively, you have this artistic stage of language design where you're thinking about the concepts for your new language. What cool new thing do I want to do that I'm going to put in this language? And having logical semantics gives you a vocabulary. It gives you a formal way to not just to talk about what the language is going to do, but to actually think. You can sharpen your thinking. You can be much more precise with your ideas of what goes into the language definition rather than any specific implementation. It's not just about human-human communication, though. Once you have stuff in logical form, as with any logic, you can then do meta logic on it, and you can prove theorems about the system. So your language is going to be defined as a logical system. We're going to define it as a set of rules. And roughly a proof is going to correspond to running a program, or at least figuring out what the program would do if it was ever run. But as with all logics, you can then do meta logic. You can take that set of rules as an object of study, and you can try and prove theorems about the set of rules. So things you would very much like to prove about real-world languages, especially in high safety security environments, are, can the language itself ever crash? Many languages will have a runtime environment, and you need that environment to be absolutely bulletproof. So this has been done for some languages, right? So ML, for example, it's been proved that the ML system itself can just never ever crash. It can never lead to a blue screen or to an infinite loop unless the user specifically tells it to do those things. Can you prove that your language specification is complete in the sense of every behavior is defined and is deterministic? There are cases in C. For example, the program we just saw, I think Matthew just wrote a program that starts by declaring int A and B, and then it says is A greater than B. Okay, that's actually undefined behavior, isn't it? Because you don't know what numerical values A and B are actually going to get in that program. The C standard leaves it open. You've declared that this thing A exists. It doesn't tell you what its value is until someone comes along and sets it equal to something. So, undefined behaviors, or a non-deterministic behavior, is where more than one evaluation is defined. If there are two different things that could happen according to a definition, you would really like to prove that your language is free of these cases, so that you actually know, in some sense, guaranteeably, that the program is going to execute in a certain way. A lot of this stuff is to do with types. Type safety or type security means that if something is given a type, it's correct, and a variable of one type can never get misinterpreted as being another type. So you can do horrible things in C again. For example, treating booleans as ints. And arguably, this is a feature, right? You can add the number 0 to the value true, and it will interpret that in some way according to Boolean logic. But in many cases, you would like to prevent that from happening. In particular, there are security issues. Many attacks will come if they find a breakage in the type system. You can then exploit that problem with the type system and start shoving in information in one type that was supposed to be of another type. Similarly, for memory safety and security, you'd often like to prove that you're not going to make a mess of the memory. And again, the C family of languages is notorious for not being secure in this way. It's very easy to write C programs where memory is getting accessed in ways that weren't intended. And that's probably still the major source of security issues in C-style programs. So these are theorems about the whole language. Yeah, does the definition of a language actually make sense? Is it coherent, consistent, complete? As with other logics. At the level of individual programs, we've already talked about verifying individual programs, but that verification process itself can be informed by understanding the semantics better. The logical rules we've seen in Floyd-Hoare logic, they're not a complete description of the language. If you remember, there's this business of a human having to choose the variance and the invariance in particular. So if you make an interesting statement in Floyd-Hoare logic, you can then show whether that statement continues to hold or not. but it's up to you to go around choosing those statements. And it's having to rely on a human to do that doesn't give you a complete description of the language. So maybe verification could be done better if we had a rigorous description of what the language actually does in the first place. If you are interested in optimizing code in particular, or optimizing compilers as well, it can be very important to show that two programs do the same thing. You might start with a program that is slow, and you are going to replace it with a program that is fast. And you'd like to make this claim that they are in some sense the same program, that they have the same behavior. And to get that concept of sameness, you need this concept of what does the program mean, what does it do, and again, you can derive that from the semantics. And the dream of this has always been to build a semantic compiler, a meta compiler. As we have for syntax and parsing, we have Flex and Bison, which can take BNF grammar definitions and automatically generate a parser from those definitions. Wouldn't it be nice if we could define what the language actually does in a similar way and feed all that into a meta compiler, and it would just generate a whole language for us? Still an active research area. It's been a research area for quite a long time now. Okay, so look, we can already do this. We're already very good at manipulating syntax. We know how to take sequences of characters and group them into grammatical hierarchies, and we have nice automated tools now like Flex and Bison that will do this with minimal fuss. But once you've created a parse tree like this, what should you actually do with it? How are you going to either interpret the language in real time, or if you're doing a compiler, turn it into assembly code to have that same behavior? So what does this tree actually mean? Beyond being a grammatical description, what does it mean in terms of describing the behavior of a computational system? There are two broad ways of doing this, as there usually is when people talk about meaning. Okay, so meaning has two meanings. One meaning of meaning is to do with what is called sense, or in this context we'll call this operational semantics. So for sense or operational semantics, we're talking about the behavior of a program, the step-by-step sequence of what happens as the program executes. Alternatively, the referent of the program, or what is known as denotational semantics, they assign a meaning only given to its final result. Okay, so you could have two programs that have the same denotation but different operations. If, for example, to multiply a number by 10, you could have one program that does it by sticking a 0 on the end, or you could have another program that actually does it arithmetically by adding a bunch of things together to compute the multiplication. So those programs would have the same referent or denotation, but they'd have different operational semantics. So here we're just going to talk about operational semantics. These tend to be more useful in actually describing the implementation of a programming language. These are what you can take and actually build them into your compiler or your interpreter as a description of what it is actually going to do, rather than just its result of what it computes. And this is the world of compiler backends. Okay, you'll often come across parsers and front ends of compilers. Very nice to teach, very nice to study, nice automated tools. The backend always seems more mysterious. This is where we're talking about the semantics of what the language actually does. So, for example, what does this program do, or what should it do?
This program should be thrown in the trash because whoever wrote it. There's this fantastic quote by Nuff. I looked it up because something you said in a thing reminded me of it, which is that programs are meant to be read by humans and then only incidentally executed by computers. I think this falls very concretely under that. Does it even matter what the abstract syntax tree comes out as when it's hell? But this, let's see. Well, actually, since you've made a distinction between operational and denotational semantics, let's go through the operational semantics of this first, and see if we can deduce what it should actually produce. So we start with C, and we do a C++. Now, obviously, C++ returns C, but it increments the value of C, right? And then we add that to ++C, which should increment C, and then return the value of C. And then we add that to something that returns C and then increments the value of C. So I think that the order of operations here, so that both ++C and C++, the order that they should be evaluated as opposed to a plus that combines two things is that the ++ should be done first. So C++ and ++C and C++ should all be added together to start with, so that we have basically C plus equals 3. I think.
Shall we take a
this is a guess.
Let's. Okay, everyone, figure out what you think is the value of C at the end of the program, and please paste it in the text chat. You have 1 minute, say. You have till 15:02 to work out what numerical value does C have at the end, and paste it in the text chat. Go.
Oh no. So I was. Oh no. So yeah, because it's actually kind of interesting whether or not the pluses go together before the pluses are together, because obviously the return value is different in either case. So it's just very.
All right, we've got a vote for 2.
2 is quite low, huh?
8.
Hmm.
Nine, 6. Any more for any more?
So I've gone through it. Oh, I'll post mine in chat as well.
7. Any more for any more? All right, Theon, how did you get 6?
You know what? I'm not 100% sure anymore, but at one point I definitely did.
I think I got 7, but I'm not sure. I don't know what the value of this either is, by the way. How did you get 9?
I am just loading C++ now, and we can find out.
Okay, look, it doesn't really matter what this actually does, and the point is to show that it's complicated. Yeah, it's not clear to a human or even to a compiler writer what this should do. Yeah, so some of the questions you might ask are should all these increments be done at the same time? Should they all be done either before the whole line value is taken or after the line's value is taken? Should we work from left to right? Should we go and figure out the value of C after doing this bit? So I think this is how I got 7, right? C++ means you increment. It means you take the current value of C. So this thing has value 1, yeah? And then you also increment C. So C now has value 2. So if you have this kind of left-right semantics, you would do that, and then you'd say, now let's go and evaluate this bit. And ++C means you increment it before you use it, yeah? That's why the language C++ is misnamed, because they were supposed to improve the language and then have people use it. But this actually means you use it and then you go and fix it afterward. So yeah, ++C means you increment it and then you use it. So if you have this left-right semantics, you've got 2, you're going to go and increment it to give you C equals 3, and you're going to use the incremented value, which is 3, right? And if you do left-right semantics again, you now take the value, which is 3, and then increment it, which is 4. So doing it that way would give you 7. Okay, that assumes you're going to have this left-right semantics. I don't actually know if that's what C++ does or not. But the point is, it's complicated.
Should
Right?
do. Yeah,
Has anyone actually executed that in something?
I've not. That's a fantastic idea.
Nope, I'm having trouble getting C++ to actually work because I've never actually written a C++ program from scratch in like over a year, and I cannot remember how to.
It is indeed 7.
In your implementation of it, at least, yeah. Different from what's in the standard.
No, I do believe that the standard does define the order, because the order of execution, the priorities of what order things get executed in within a statement that's joined, is defined in the standard. It is now actually. That only happened in C99, so which is actually a fairly recent version of C. Until then, it was just kind of implicit.
Right. So for the first couple of decades of C, we were building nuclear missile control systems and stuff where this could actually have been 6 or 9 or possibly 7 or 8. Yeah.
I think it would depend on. So let's say if you weren't using plus, for example, if you were using different operators. So if it was a plus and a minus, or a plus and an or statement, different compilers might put that or statement higher or lower than other ones, even though like Booleans and arithmetic should have very clearly separated. Yeah, but obviously in C they're similar. So
yeah. Okay, so the point is, it would be nice to A, define this properly, and B, to be able to prove that it was fully defined properly. Yeah, so this is A, and then the meta logic could provide formal proofs that we've covered all these cases and that the definition is actually complete and consistent. So let's look at operational semantics today as a way of doing that. We're going to introduce a logic with a few extra ingredients. So as with all logics, it has some special symbols, and we're going to give those symbols certain meanings. If Floyd-Hoare logic was another approach to doing this, where we created a mixture of programs and assertions. Did you get 7 as well?
No, I got 8.
Hell yeah.
Hang on, wait. Who put it into C++ and got 7? What code did you use?
You'll love to
Just
see
copy
it.
Just because I literally put this is the main function I have for mine. Just pretty much what it says on the tin.
Right.
I will take my prize money in a check. Thank you.
Okay, I will write you a check for 0.
plus
Okay,
zero.
so let's introduce some extra logical notation. Right, we are going to be talking about imperative languages here. Not quite for the first time, but we need a notation for describing the state of a machine. So let's assume we have a very simple model here of memory. This is like a Python dictionary. It's got a bunch of variable names and it maps those variable names to their current values. Okay, so here x has the value 3, y has the value 4. Why is this a simplification of real languages? What can you do in C that you can't do here?
Provide type information, I believe.
Yeah. Okay. No types yet. Yeah. So you also can't do pointer arithmetic, right? There's no concept of where x is in the memory. In C, x and y might be located next to each other, and if you add 1 to the address of x, it might take you to y. So we're not going to have any of that. We're just going to have symbols that are mapped to values at this point. Okay, so let's call this state. Then we'll have expressions from grammar, as we've seen before. So we're happy with expressions, and then we'll call a configuration a pair of an expression being evaluated in a particular state. So an expression can take different values according to the state you're in, because the variables in it will have different values. And then we'll talk about transitions. And a transition is a step of computation. This says if you're in state S looking at expression E, and you do your computation, this is what the language is supposed to do. It's going to evaluate that expression in that state, and the result is that it goes to E prime S prime. So this is a formula of our logic. Now these are a bunch of symbols. Every logic has a set of symbols and rules for making formulas. And assuming you've got a grammar already for your expressions, this gives you a grammar of formulas. We'd like to know which formulas are true or provable, which are hopefully the same thing as usual, and which are not. So we can look at a transition like this and we can say, is it true? Does expression E in state S actually go to E prime S prime? Or equivalently, if we state this as an axiom, then we're defining what the language is going to do. We're saying that's what it does. That's how it will be evaluated by any language that meets the specification. So, as always, a theorem is a formula that is provable and hopefully therefore true. Let's consider a little tiny language as an example. By the way, the content of this lecture is largely shamelessly ripped off from these two sources. This is a Cambridge module on semantics. This is the book Concrete Semantics by the authors of Isabel. Quite hard to find books on this stuff, often just passed on through lectures from generation to generation. So L1 in particular is taken from the Cambridge example. So L1 is just language 1, right? It's a tiny little imperative language. So here's a grammar for a bunch of expressions, and they bottom out into certain fundamental entities. So we're going to have Booleans. Booleans can be true or false. We're going to have integers. We're going to have memory locations. Okay, these are symbols L, L0, L1, L2. They're the variable names, effectively. And we'll have some operations. We'll just have plus and greater or equals. Okay. So from those basic ingredients, we're then defining expressions here. So an expression can be a primitive thing. It can be a number. It can be a Boolean. It can be an expression, operation, expression. So what's a problem with this, by the way? Remember, we're not doing types yet. We're going to look at types later on. What could happen here that is potentially bad?
Is it that because we haven't got any information about what those two expressions are, then if one of them has a different type to the other one, and those types aren't compatible, then performing that operation is invalid?
Yeah.
Is that...
So we're going to get horrible things like 3 plus true at this point. That's why we might want to put in a type system later on. Good. Good.
No, well, this is still at the syntactic level, so
Yeah.
it's a different degree of abstraction, isn't it?
Yeah. Yeah. So yeah, that could be syntactically valid, but not semantically valid. Good. Okay. So we'll have an if statement. We will have memory. We will have assignment. So here we're going to say you can set the content of a memory location to something, and you can dereference it. So these bars are just separating. Let me draw that differently. These bars separate the different expression. So that is an expression and that is an expression, right? This is if you're assigning the content of a variable to an expression. That means go and evaluate E and put the result in L. And this means dereference it. This is find the value at location L. We have skip that does nothing. We'll have commands written with a semicolon to describe doing something, then doing something else. And let's have a while loop to make a little language. Okay, so this is an example of how we can define semantics for this language. Rather than just going and hacking a load of code in Flex and Bison, the idea is, as a human, we're going to first write down these rules, and then we'll implement the rules in the back end of our compiler or interpreter. So some of these are axiomatic. You could draw these equally with a line above them, just to show that they don't require any premises. And some of them are proof rules that have a premise and a conclusion. So we're going to say, if you've got two numbers, and remember n is only integers, yeah? If you've got two numbers and the operation of adding, and it doesn't matter what state you're in, you will always get the result where n equals n1 plus n2. That's a little bit of English meta logic sat alongside the rule. So this just says whenever you have two numbers together with an add, they get added. Okay. So what about this one? What is this one doing?
This is saying that applying the operation to n1 and n2, and given that B provides that the solution to that operation, then return B and all of the other state that was alongside it.
Remember, B is a Boolean, yeah? So the semantics for this integer operator integer, in this case it goes to the Boolean B, and the particular value of it is given by whether or not it is the case that n1 is greater than n2. So notice this is a semantic thing. Here you've got to go into your model theory and ask what that number actually is and what it means. That's going beyond syntax. That's why we had to write it as a bit of English on the side. Okay, so what's going on here then? Let's take a look at this one. So here you've got any expression and any other expression with an operator in between them. Okay, so remember here we were only dealing with numbers. Here we're saying what if they're not numbers, what if they're arbitrary expressions? And we're saying this is going to evaluate, or this may evaluate. At this point the rules are just saying you can derive these execution paths. You're saying this may evaluate to this if the stuff up above is true. And you can see what's happened here is that E1 has been reduced to E prime. Okay, so E2 has stayed as it is, and E1 has done some reduction. It's done some computation. So you're allowed to go from being in this configuration to this configuration if E1 by itself will evaluate to E1 prime. And the state may change as well as you're doing that evaluation. Okay, so this is telling you if you've got a big expression added to another expression, for example, you are allowed to go off and evaluate just the left-hand side of that first. And that evaluation may have side effects, like we saw in that C++ example, right? That may change the value of a bunch of variables. So if you do that, you've got to update the state as if you were just evaluating E1 in the state. But there is potentially some ambiguity here, because should you go off and evaluate E1 first, or should you go and evaluate E2 first? Okay, and if these expressions have side effects, you may end up with different answers. So you need the semantics to be unambiguous on the evaluation order. Matthew?
Doesn't this reduce that ambiguity? Because on the right-hand side, you're not doing E2 prime, you're just doing E1 prime. So you're only evaluating E1, right? So there is no ambiguity,
Okay.
surely.
So this rule is only letting you evaluate E1. Yeah, it's saying if you've got two expressions with an operator, then you can go and do the left one. Yeah, good. It's not saying anything about E2 yet. So this language has actually been designed quite carefully to reduce that ambiguity. You can see this next rule, it has the same input form, but here we're talking about when you're allowed to change E2, okay? And look, this is the right-hand side. This is saying you can only go and reduce the right-hand side if the left-hand side has finished. If the left-hand side has stopped being an expression and it has now become a value. Okay, so when this thing's become a value, you can't reduce it anymore. You've done all the work that you can do on the left-hand side. So together, this is one particular language, right? There are other ways to set up semantics for a language. In this language, the rule is you must go off and do all the work on the left-hand side first until you've got a value. And then when it's done, then you're allowed to start reducing the right-hand side. And that's a way to remove that ambiguity. You know, that's exactly the kind of thing we had, right? Where you've got this, you know, C++ plus C. You know, it's telling you that you have to go and do all the work on the left-hand side first, and that includes changing the value of C, updating the state of C. You're going to do all that work first, and then you're going to go and do the right-hand side, and that will inherit whatever state came from evaluating the left-hand side. So, you know, if the C standard had something like this in the first place, we wouldn't have had to have that big argument about the value of the expression. Matthew?
I'm interested. So we've defined these plus and greater than or equal to operators. Surely if we've defined the whole range of operators within our language, then something like that last one isn't necessary, because at the point of which it's a value and then an expression on the right-hand side. Oh no, that's not true, because you could have like a sub-expression, so we could have like brackets around. Okay, so what I was going to say is, surely the case in which opt2 is actually useful is already defined by all of the operations that we defined before, but that's not true in the case where you have something on the lines of, say, 3 plus open brackets, 2 plus 1 close brackets. You'd have to define the right-hand side expression before you can evaluate like the whole thing. Yeah, that makes sense.
If you're only doing addition is commutative and associative, so it doesn't matter really what order you do things in, right? But if you've got programs like this, suppose your expression is a program, and it might say assign x to 1 and then use the value of x. So this program has side effects. If that x equals 1 is going to change the state of the machine, and that state could then affect how the right-hand side gets evaluated. So this is really important for languages with side effects, when it becomes critical what order you evaluate in. If you have no side effects, then you've basically recovered lambda calculus, and by the Church-Russell theorem, it doesn't matter what order you do the evaluations in. When you have the side effects, when you have this state, then it becomes important to update the state in the right order. Okay. Okay, let's look at some more rules from this little language. So again, you can read these as axioms, you can read them as if they've just got a big line above them. And this is English conditions on the side. So this rule is telling us how do you dereference L, okay? Dereference L evaluates to integer n if and only if the integer n was actually stored at that location. These are the semantics. You have to go and look at the model theory to do this part. This is the syntax. How do we do assignment? That's the other way. Here we're saying make the content of L equal to n. And that is going to evaluate to this. So skip means don't do anything. If this expression itself has no value, it doesn't have the value n or an integer, it's just got the value of skip, which is nothing. But it has a side effect, which is defined by this. You're saying the state has now acquired this extra element that L is mapping to n. That's the base case for assignment. That's if you assign L to an integer n. What if you've assigned L to an expression rather than an integer? This rule tells you you can do that if and only if you can evaluate that expression. Okay, so you're going to take that e, you're going to go off and find its value. You're going to find that it evaluates down to e prime. And then you're going to replace it with assignment of that new value. Okay, so this is not the case in every language. There are Lisp style languages, for example, you can say x equals some big expression, and then it just equals the expression. It equals the string almost of the expression. But in this language, we're saying if someone says, if someone says L becomes equal to 2 plus 2, we're not going to store the symbols 2 plus 2 in memory. We're actually going to go off and evaluate the symbols first. So you have to take that expression, you reduce it down, you reduce it to 4, and the thing that actually goes in memory with name L is the number 4. It's not the expression 2 plus 2, it's the evaluated result number 4. Okay, and then these are rules for giving sequences of commands. This is an imperative language, so we are hitting on memory and we're doing sequences of commands. So this says skip doesn't do anything. Okay, if you've got a skip, then you can just delete it and replace it with whatever came after it. And if you've got E1, E2, this tells you you are going to go and evaluate E1 first. Okay, so again, compare this with lambda calculus. In lambda calculus, you could go off and start doing work on the second part of your program right at the beginning, and it doesn't matter the order you evaluate in. But this one is saying if you've got a command or an expression followed by another expression, it's saying you must go and deal with that expression first. You evaluate it down, keep evaluating it down, and that's all you're allowed to do with it until it's turned into skip. And if it ever turns into skip, then you're allowed to get rid of it, and only then are you allowed to start thinking about E2. You could imagine, now we have parallel compilers, you could imagine languages where you have 10 lines of code written in a row, and you might try and evaluate them all simultaneously. In some languages you can kind of do that to varying extents, but these rules are saying you're not allowed to do that. You must evaluate one command and then go on to the next one. All right, then we've got finally some rules for control in the language. So these rules go together. This is describing the semantics of if. So base cases, if true and if false, simply say that you're going to pick out one of the other two expressions, right? An if statement takes three sub-expressions, one here, one here, one here. And if this one's true, then you're going to replace it with the first expression. If it's false, you're going to replace it with the else expression. Those are the base cases. That's if you know the Boolean value. If you aren't given a Boolean value, you're given an expression here. So this rule says, in this case, before you think about E2 and E3, you have to go off and prove this. You have to find out what E1 actually reduces down to. So this rule says you can do as much reduction as you like on E1. You plug in the result there. So you can keep on applying this rule to reduce it as much as you like, and then eventually you'll get to one of the base cases, and then you apply one of the first rules from up there. You've got one for while. So this is given as an axiomatic rule. Or this is neat, actually. If you get this, you can appreciate it. This is given as an axiomatic rule on the top of the line, and it turns the while into a recursive if and another while. Okay, so yeah, what's the meaning of while E1 do E2? It is if E1, then do it all again, and otherwise stop. So this is a recursive definition of while. Question?
Yeah, that's very pretty, but I see that at the end of it, the state is not modified. So I know that we don't have any evaluation of E1 or E2, but surely, intuitively, if we're doing a while loop, the side effects are kind of like the point.
Oh, that is good. That is very good. Yeah. L1 is a made-up language, so we're allowed to define it however we like. Yeah, maybe that's not a very good way to define a language, is it? Because you really do want this to change, don't you? Yeah. You really want to go off and evaluate. What are we actually going to do? We're going to evaluate E2 here, aren't we? Oh, although I think this does actually work. If you'd have to do this with a pen. What this is going to do, this is a single rule, right? It's not starting with something at the top and going to the bottom. It's simply saying you replace
so this is going to
with,
expand it to a bunch of expressions, and then each of those individual expressions, this is basically just going to expand it to a bunch of if statements, and then we do have rules for evaluating and editing the state within if statements, because that's what we've defined in if3. Yeah, okay.
Yeah. Ah, it's even cleverer than you first think. Yeah, so when you actually go and reduce that, then you'll use one of the other rules to update the state. Okay, good. Okay, so look, this is a really tiny language, right? And you can just about imagine writing a little program in it now. It's the kind of language you might write as a student compiler project, for example. But when we treat the language itself as an object of study, it is actually pretty complicated. You could hack this up in Flex and Bison and have something that you think has implemented this. But yeah, you can see there is subtlety, right? These questions of how exactly are these left-right orderings going to get executed? Exactly what order should the commands be executed in. It's not, from the point of view of logic, it's not obvious that you have to run one command and then run the next command. When you look at functional languages, or lambda calculus at least, you can do work on evaluating many parts of them in parallel. And in many cases, we would like to do that because we have to make things go faster by doing them in parallel. Yeah, exactly what is going on here. Where do the side effects of the while loop fit in? So, really understanding a set of semantics like this is a very non-trivial process. And let's go back to some of the objectives we had at the beginning. We'd really like to prove that the language itself is a good language, and that means it means proving that the language will always execute. It means proving that something will always be done if we give it an expression. It's not just going to run out of rules to apply and hang there. We also want to prove that it's deterministic and that there aren't two different rules that could kick in at the same time and compete against each other, wanting to be executed. And hopefully these rules have now covered horrible cases like doing 3 plus true. We would hope, what would actually happen? I think in this case the language is, there are cases where the language will just hang. I think if you put in 3 plus true, there just isn't any rule for executing that. You can't run this rule because it only works if you've got int plus int. So maybe this L1 language isn't as good as it could be because we found there's a hole in it. So we'd really like to use meta logic and automated tools for meta logic to try and prove these things. Can we have a system where you give it a language definition in terms of their semantics and it tells you, yes, this is a deterministic language, and yes, the language has progress. The progress property means a computation will always occur and you'll always reduce down to a value. So we don't have time to go into how this is done. The very short version is done by induction again. Induction is this general method of proof where you show that P holds for a bunch of base cases, and then you say that under each rule, if P used to hold, then it still holds afterwards. And so roughly, you're going to take easy cases. Let's find some easy cases. These are base cases. For example, here the Boolean is bottomed out. You might prove that all the properties hold for these easy cases. And then you say, if it already holds for an easy case, can you show that it will always hold for the more complex case given by applying one of the rules to that easy case? So imagine you're coloring the theorems in red. Okay, every time you prove a theorem, you color it in red, and you want to prove the fact that all theorems are red. So you start off by coloring in the axioms red, and then you look at the rules and you say, does every rule have this property that if the input is red, then the output is also red? And if everything's red, then you've proved that the whole language is going to be red. So instead of redness, you have these properties like determinism and progress, and you're going to use that induction to show that they hold across the whole language. Probably you're not going to do that by hand anymore. Probably you're going to use one of these automated logic and computation tools like Isabelle or Cook. Let's have a little chat about functions and then we'll have a tea break. Yeah. So yeah, the main place you will see semantics discussed as a user of languages tends to be around functions. So for example, what does this do? Let's do the text chat thing again. Go on, you've got 1 minute to figure out what this does, or equivalently in a human readable language. This is just the lambda expression with some sugar.
It sets some free variable c to 2 and then sets it to 1. As far as I can tell.
So what is the value of c after executing this expression?
I believe it should be 1.
Do you guys want to vote in the text chat? Let's see, vote for 1. 1. Any more for any more? Looks like it inputs c equals 2, but then overrides it. I'm surprised. No one voting for 2? So look, say you did this in Python, yeah? Or C even. What's the value of this expression? This c equals 1.
Well, this bottom one looks a little bit different though, I think. Because in this one, you'd evaluate c equals 1 and then put 1 into that. But then you have this floating value c within the function. It's not setting x or anything. And then it returns x. And that return, the return value isn't really used. So this is...
So in C, what value are we actually passing to this function? And we call the function here.
Would be giving it x equals 1, right?
Mm-hmm.
So within the function, x would become 1. So we have c equals 1, and then, but c equals 1 would return 1, right?
Okay.
And then we give my
okay.
function 1.
When we ask what it does, there's actually 2 things going on then. Yes. So one is what's the value of the expression? So I think we all agree the value of the expression is 1. What else does it do? What is the value of c at the end of the execution?
Well, I think it's different for the two of them. Oh, so going back to this lambda expression thing, that colon equals thing, is that explicitly referring to the side effects?
Yeah.
Okay.
Yeah, this is assignment. So this isn't actually lambda
Then,
calculus. This is
okay, so first thing that's going to happen then, never mind, c gets set to 1. And then we have this function, and then we're going to set this x value to 1 as well. But then we're going to set c to 2, and then x is going to evaluate to 1, and the function's going to return 1, but c is going to be 2. Is that what I'm reading?
So you're going to go for what the total value is 1, but the side effect is c equals 2.
Eventually, because first we set it to 1, and then then within the function we set this free variable to 2, and then we return this x variable, and here this x is 1.
Okay, so I think you're looking at something like this. Okay. This is what's called call by value execution. So what you've done here is you've taken that argument, you've evaluated it first, okay? So the value of this expression is 1. Sorry, the value of c after executing this is 1. The value of the expression itself is just nothing.
Well, no, it's oh, okay. Well, so within L1 that would be the case, but within C, if you set something to 1, that equals also returns what the value of the thing is?
Yeah.
After you do that evaluation?
Yeah, okay, so in C it would also take the value 1, wouldn't it? It would set C to 1, and it would also take the value 1. Okay, so yeah, okay, let's look at what happens in C then. So at this point then, the argument, let's say this is C, the argument is going to take the value 1, yeah? So that means that x is going to take 1 in here, yeah? And so you're then going to execute the lambda expression. So this is going to have the command assign c equal to 2, yeah? So it's going to do c equals 2. And then it's going to execute x, which in C, this would have taken the value 1, yeah? In L1, it's taken the value skip, and you've got skip sitting in there. Either way, the side effect is that C ends up with value 2, because the last thing we did to C was set it equal to 2, yeah? Elliot?
Would it be possible though that you're setting the value of x to be the function c equals 1? So that by returning it, you're returning C equals 1 instead.
Yeah, absolutely. Okay,
Ah.
so these are alternative semantics. Okay, so these are extra rules that implement what you've just seen for call by value, right? If we instead choose these rules, we get call by name semantics. Yeah, good question, the right question. Yeah, in call by name, we're going to take this thing as an expression. Okay, we're not going to evaluate it yet. We're just going to take it as an expression. So C itself is undefined at this point, and we just got that expression. Yeah, absolutely. So this is more like lambda calculus style, arguably. You're going to plug that whole thing straight into X, yeah? And so at this point, we evaluate the lambda expression, and that means that C becomes equal to 1 gets plugged in here, yeah? So that whole lambda expression now says make C equal to 2 and then make it equal to 1. And yeah, when you execute these, you'll now set it to 2, then you'll set it to 1, and the end result of that is that C is taking the value 1. Okay. So the answer to this is it depends, right? What does this do? It depends on what semantics are being used in the language. This isn't an official language, neither is this. I've just written this in some kind of vaguely C or Python-like notation, and this in a vaguely lambda-like notation. This isn't lambda calculus because you've got assignments in it. Yeah, so the answer is it depends. You have to define the semantics of what you want these programs to do. And here are extra rules we could add to our L1 language to implement call by value or call by name. So in call by value, we are basically saying these are application rules. Yeah, we're basically saying you have to go off and evaluate the argument first, and then plug it into the function. So this is just a rule, as in lambda calculus. This is just saying here's how you evaluate a lambda expression. You take a value v, and you go and substitute it for x in the expression. What are we saying here? Look, if you've got an expression applied to another expression, we're saying you can always go off and evaluate the left one first. And if you've done that, if you've got a value from that one, then you can go and evaluate E2 second. So you have to sequence evaluating this thing. You're going to reduce this down and then plug it in to the lambda expression, whereas in call by name, you're going to go the other way. In call by name, you're just going to take that thing, you're going to take the whole expression as an argument, and you're not going to evaluate it yet. You're going to go plug it in first into the lambda expression and do your evaluation coming later on. So has anyone ever come across?
What I'm learning here is that you should never have side effects in a call by name system ever, basically, because then you're propagating the side effects down into the inside of the thing, and it's just terrifying.
Yeah,
this is why pure languages that are lazy almost never tend to have side effects unless they're explicitly removed from it. I think like monads.
Yeah, this mixing of side effects and assignments and evaluations can get very, very messy. Yeah. Has anyone ever come across any other forms of function semantics? Call by name and call by value are the main ones. You might have heard of a few others in other languages. So if you have languages with pointers, you'll come across call by reference, for example. That means you're passing a pointer to an entity rather than passing the entity itself. And there's another one called call by need, which is a little like call by name, but you only have to evaluate the thing once. Call by value can be quite wasteful because you might call f of x where x is some giant thing that requires loads of computation, and then it turns out you never actually need to use the value of x. So this is called strict evaluation. Yeah, it's strict because you're doing all the computation work. So strict languages will normally run slower, but they're much easier to reason about and to make sure that programs actually work. Whereas in a lazy language, lazy is any evaluation that is not strict. So that includes call by name and call by need. In a lazy evaluation, you're pushing the work of evaluation later on. So call by name, if you've got a function that takes x and it uses x a bunch of times, every time it appears, you're going to have to go and evaluate it. In call by need, you say wait until it actually shows up in the body of x once, and then you evaluate it once, and then you keep that value, and you use a copy of it for all the other ones. So you find there's a trade-off in language design. Do you want a strict call by value approach that makes your language very rigorous and correct, but possibly slow to implement, or slow for programs to run? Or do you want a lazy language which can run faster, but is going to make it much harder for you to provide the guarantees that things actually work? So we're going to have a cup of tea for 10 minutes, and then we'll come back and talk about types at 4 o'clock.
Mhm.